There were many themes in the astronomical year 2023, but the one that perhaps most touched me personally is the renewed interest in our local galactic neighborhood. I said in my previous end-of-the-year video that I felt our galaxy does not get the attention or affection it deserves from us, the ingrates who live in it. This is partly because we can't see it, so in acknowledgement of that, here's a picture of UGC 12158. A galaxy 384 million light-years away that is, as far as we know, the closest we can get to seeing our own in a mirror. This year, however, in part thanks to the revelations of the Gaia probe, our galaxy and its immediate environs have been subject to an adoring level of scrutiny, clarifying and securing our place in this vast universe. As a rule, I don't like to announce future projects in advance, mainly because whenever I do, they always end up not happening. But, assuming I can track down the necessary research material, I have a tentative collab lined up that, once the next video in our local stellar neighborhood is published, will extend our journey to our local family of galaxies. Consider this, then, the primer. Our local group of galaxies is something of a social climber. The word group grants it pretensions of astronomical majesty, when in reality it's just two galaxies, the Milky Way and Andromeda, in the process of collision, each dragging along a retinue of smaller followers. Our galaxy has a few dozen hangers-on. The exact number is difficult to determine because it is unknown precisely how many are actually in orbit, while Andromeda has 13. This is all but certainly a vast undercount, since Andromeda, which is larger than the Milky Way, is likely to possess more satellites. For years, the default position on these satellite galaxies is that they were essentially planets, stably orbiting, established companions in a long-term gravitational system. There from the beginning, there until the end. But an examination of Gaia data released in 2020 has questioned that assessment. Gaia mapped the motions of 40 dwarf galaxies in the vicinity of the Milky Way, and from them, a French team was able to determine their orbits, and thus their orbital velocities and angular momenta. To their surprise, these values were far higher for those galaxies than for other objects orbiting the Milky Way, such as stars and globular clusters. Since the Milky Way's tides gradually sap orbiting galaxies of energy and momentum with each orbit, these orbiting galaxies must have arrived relatively recently, within the last few billion years, or, in their terms, just a single orbit. This shows that very few of the galaxies in orbit of our own are actual satellites, rather that they are in death spirals that will ultimately lead to their tidal dissipation and then consumption by our galaxy, unless their velocity is high enough to smash through the galactic disk, though even then they are unlikely to survive unscathed. The main reason our local group of galaxies is called the local group, instead of the Milky Way, Andromeda, and hangers-on, is the Triangulum galaxy. Unlike the malformed dwarfs comprising most of our local group, Triangulum is a fully fledged spiral, with a mass 5 times larger than its next largest galaxy, though still less than 5% that of the Milky Way. Nonetheless, it is tempting to feel sorry for it, as it is usually seen as a satellite galaxy of Andromeda with ideas above its station. In 2005, astronomers used black hole water lasers to determine Triangulum's motion, and found that it was moving towards Andromeda, suggesting that, like the satellites of the Milky Way, it was not long for this dance. But this year, James Webb set a record when it observed for the first time star formation in Triangulum's spiral arms. At 2.7 million light-years, the farthest such events have ever been observed, and the first time they have been observed in a galaxy like our own. Stars hide their birth agonies behind clouds of dust, which refract their light into the infrared. This makes infrared telescopes like James Webb ideal for spotting them at great distances. The team noted that Triangulum's spiral arms were flocculent, a word that just means woolly or fluffy, possibly due to star formation affecting the gas clouds within. Given that it's the one we live in, you'd think our local group of galaxies would be fairly well mapped, and for the largest objects, it probably is. But, like the scattered debris at the edge of our own solar system, those stray urchins in the cold of intergalactic space do occasionally still swim into our ken. And in November, a Canadian-led team of astronomers discovered the faintest member yet. Dubbed Ursa Major 3, or Unions 1, after the survey that located it, the galaxy, although this is not the right word for it, has an absolute magnitude of 2.2. Absolute magnitude, for objects outside our solar system, is defined as how bright an object would appear assuming a viewing distance of precisely 10 parsecs and an unclouded line of sight. For comparison, the Large Magellanic Cloud has an absolute magnitude of 0.9, or a little over 3 times brighter. Unions 1 is highly compact. Its half-light radius, the point at which its luminosity decreases by half, is just 10 light-years, and is believed to comprise just 60 stars. As such, Unions 1 is best described not as a galaxy, but as a cluster similar to the Pleiades, though the Pleiades has many more stars than Unions 1. Unions 1 orbits our galaxy at a distance of about 43,000 light-years, and every few eons passes through its disk at a distance of around 52,000 light-years from the galactic center, or about double the orbit we're on. The stars of Unions 1 are metal-poor, and believed to be at least 11 billion years old. Current consensus asserts that our galaxy, at least by galactic standards, is quite big, with estimates placing its mass at around 1 trillion solar masses. But if new Gaia data are to be believed, this was a gargantuan overestimate, and the Milky Way actually weighs in at a far slimmer 200 billion solar masses. This is no minor adjustment. The implications of this discovery are profound and potentially earth-shaking. Prior to Gaia, measuring the rotational speeds of stars in our galaxy, better known as its rotation curve, was hampered by the fact that we were inside it, which has limited the range of our vision and obscured the motions of stars. But with Gaia's third data release, we now have a far more accurate map of our galaxy's components, and the findings are, frankly, unsettling. To understand why, we must go back to one of the stars of my channel, Johannes Kepler, who, in 1618, discovered a fundamental law of nature. The further a planet was from the sun, the more slowly it moved. Isaac Newton later expanded that law to the entire universe, and showed that the gravitational attraction of an object decreased exponentially with distance. Today, any system that follows this law, such as our solar system, is said to possess a Keplerian decline. Everyone expected our galaxy would do the same, but in 1978, Vera Rubin, who will soon have an observatory to her name, realized that whatever rules our galaxy followed, Kepler had not been informed. Rather than rapidly decrease in speed over distance, the stars in our galaxy actually sped up. The simplest means to reconcile this discovery with theory was to assume that a vast reservoir of mass surrounded our galaxy in a halo invisible to our detectors. This substance, whatever it is, has evaded our eyes to this day, and gained the inaccurate moniker dark matter. One thing to note about that map, the standard image illustrating Rubin's discovery, is that it extends to only 50,000 light-years, which is about 15 kiloparsecs. The improved Gaia map extends the galaxy's rotation curve out to 25 kiloparsecs, and it is in these distant regions that Vera's vision begins to cloud. Rather than maintain or increase the huge orbital speeds, the stars of our galaxy fall into a predicted Keplerian decline, much as the planets in our solar system do. It's as if classical physics were hiding behind a hill, waiting to be rediscovered. To be clear, this discovery does not disprove dark matter. It merely suggests that our galaxy has far less of it than previously thought. But if its distribution in our galaxy is at such variance with prediction, what does that say about its presence in other galaxies? Is our galaxy a freak? Or will such precise studies find similar curves across the universe? Could we be looking at the first glimpse of dark matter itself, or the first thread of its final unraveling? There is a misconception that galaxies rotate like this. In fact, they rotate like this, Or at least so we think. Unless we crack immortality, it is a hypothesis we are unlikely to successfully test. If galaxies rotated a la a merry-go-round, then their spirals would eventually become tighter and tighter, as those stars near the center outpaced those at the edge, until the arms disappeared. Spiral arms, to last as long as they have, must be akin to traffic jams, concentrations of matter that persist, even if the matter within them changes. Imagine a great wave, apparently motionless, yet constantly replenished by unrushing water. These traffic jams are, in reality, more akin to multi-car pileups. As hydrogen orbiting the galaxy strikes the wave of the spiral arm, it compresses until igniting in a wave of star formation. In a galaxy such as our own, spiral arms are the primary locations of star birth. And it is this fact that inspired Keith Hawkins, an assistant professor at the University of Texas, Austin, to invent an entirely new way of mapping our galaxy from within. Young stars, as anyone who has been following my channel for a while knows, possess in their atmospheres far more of the elements heavier than hydrogen and helium, what astronomers confusingly call metals, than older stars. This is because when stars die, they release heavier elements into interstellar space, which are then captured by younger stars as they form. So, Hawkins reasoned, all he had to do, armed with Gaia data, was map out the amount of metals in the atmospheres of stars within the 10 kiloparsec region such data was reliable, and see what patterns emerged. He found, unsurprisingly, that his metallicity map overlapped with the expected locations of the spiral arms. But also, more surprisingly, because spectroscopy does not rely specifically on identifying the light from young stars, it revealed portions of the spiral arms that, to date, had remained obscured. This marks the beginning of what Hawkins calls a new era, as Gaia continues to map the stars and new and more powerful telescopes see first light. Chemical cartography, as this method is known, could become a standard means to explore our galaxy. This year also saw the publication of another, far cruder map, if potentially no less revelatory. Neutrinos are elusive little buggers. In the time it took you to hear this phrase, 100 trillion of them passed through your body unnoticed. The cliché is that they could pass through a light year of lead unaffected, so it seems odd that we would attempt to catch them in observatories. But the laws of probability being what they are, given neutrinos' utter ubiquity, sooner or later, chance alone dictates that they will interact with, well, something, and those fleeting interactions can be detected, though not usually in the ways one associates with astronomy. Your classic neutrino observatory is a tank of dry-cleaning solution buried under a mountain. The Ice Cube Neutrino Observatory has classier pretensions. It lies in Antarctica, the new des res for high-end telescopes. In fact, it lies at the Amundsen Scott South Pole Station, which is exactly where it says it is, nearly 3 kilometers above sea level, and comprises 5,000 separate detectors located under roughly a kilometer of virgin Antarctic ice. Neutrinos, being neutral, are unaffected by the sea of electromagnetic radiation that suffuses interstellar space, and so march in perfect straight lines, which can thus be traced back to their points of origin far more easily than the cosmic rays that produce them. Cosmic rays, rogue protons usually created by supernovae beyond our galaxy, strike the atmosphere all the time, leaving neutrinos in their wake. But with a little algorithm and machine learning, it is possible to filter out their effects, leaving only the lower energy neutrinos from within our own galaxy. And in June, that is what an international team of 350 scientists did. For the first time, the galactic plane was painted in neutrinos, showing the sources within the galaxy for high-energy cosmic rays. Unfortunately, this image was too low-res to come to any definitive conclusions, but it's a first glimpse with a new eye, and will only get sharper from here. One thing the current era of galactic astronomy keeps hammering home is that our galaxy is much, much larger than initially thought. The Milky Way, presumably like many other galaxies, comprises several regions: the famous spiral arms, where we live and from which we strain to grasp its form, the central bulge, which is composed mainly of old red stars and so has ceased star formation, the thick disk, a fog of ancient low-metallicity stars surrounding the spiral arms, and the halo, the roughly spherical cloud of stars, gas, and presumably dark matter that surrounds it. One type of halo star has proven particularly fortuitous: RR Lyrae stars. RR Lyrae stars are similar to Cepheid variables, stars that have moved off the main sequence and have begun their journey towards red gianthood. Like Cepheids, RR Lyrae stars pulsate in time with their brightness, making them excellent standard candles, though, being slightly smaller, they are only viable at local distances. In January, a study employing the Canada-France-Hawaii telescope determined the distances of 208 RR Lyrae stars and discovered they range from between 20 to 320 kiloparsecs, or between 65,000 and 1 million light-years away. This was roughly in accordance with theoretical models, which has suggested the galactic halos should extend to about 300 kiloparsecs. But it is nonetheless a bit of a spine-tingler, particularly when you remember that Andromeda, which is on course to collide with the Milky Way, is only 770 kiloparsecs away, and likely possesses a halo as large as, or larger than, our own. The hand has been offered. The participants are circling. The dance is about to begin. There is something simultaneously ennobling and silly about the Fermi paradox. On the one hand, it represents the highest leap of rational inquiry, daring to scientifically frame the most esoteric of questions, to place within our grasp the domains of gods. On the other hand, it highlights the human-centered assumptions we employ to outline a topic about which we know nothing. As an example, take its name. Please. There is no reason to assume that the lack of other intelligent life in the galaxy, however unlikely we may believe it to be, is a paradox. Life may simply be rare, and the reason may be shockingly mundane. Life, as we know it, Jim, is overwhelmingly composed of 6 elements: hydrogen, oxygen, nitrogen, carbon, sulfur, and phosphorus. 97% of life, 97% of you, are made of these 6 base ingredients. Throw in some calcium, mainly for us vertebrates, magnesium, a little chlorine, and of course some iron, and you have the beginnings of a living thing. Of the elements necessary for life, 7, hydrogen, oxygen, carbon, iron, nitrogen, magnesium, and sulfur, are among the 10 most abundant in the universe. This matchup is especially striking when you consider that just 4, oxygen, hydrogen, magnesium, and iron, are present to any great degree in the Earth's crust. You may have noticed that one vital element failed to make either top 10. Phosphorus. Phosphorus is not especially rare as elements go. With a cosmic abundance of about 7 parts per million, it is 100 times more abundant than copper, and nearly 2,000 times more abundant than tin. But it fades into insignificance next to life's other elements, 1/10 as abundant as calcium, and less than 100th as abundant as nitrogen. Phosphorus is fundamental for life as we understand it. Every link in the DNA helix contains one phosphorus atom. Adenosine triphosphate, ATP, is the chemical battery that stores and then releases energy from the breakdown of sugars, moderating the reaction and allowing us to burn calories figuratively rather than literally. If it were unevenly distributed across the galaxy, that would go some way toward resolving the Fermi paradox. And for a while, that appeared to be the case. Phosphorus appeared to exist within a habitable zone of the galaxy, between 6 and 10 kiloparsecs from the galactic center, which, by a staggering coincidence, also comprises our solar system. Except, perhaps the sarcasm was unwarranted, because, in November 2023, a team of scientists located both phosphorus monoxide and phosphorus mononitride in the gas cloud WB89621, a whopping 22.6 kiloparsecs from the galactic center, more than double the distance of the previously farthest known sample. This has been something of a shock, as phosphorus is believed to be primarily created in Type II supernovae, and Type II supernovae are almost non-existent beyond 13 kiloparsecs. The team speculate that phosphorus may be generated in the pulsing death throes of the smaller stars in the periphery. If that is the case, then the idea of a phosphorus habitable zone may have to be shelved, alongside all the other failed explanations for the Fermi paradox. Of all the galaxies in the Milky Way's retinue, the two Magellanic clouds get the most press, largely because they are visible to the naked eye, and have formed part of the mythologies of many Southern Hemisphere cultures. Not ours, because we can't see them, hence why they're named after a guy who died trying to forcibly convert the natives of the Philippines. Although not the closest of our galaxy's satellites, the Sagittarius dwarf and the Canis Major dwarf are now known to be closer, they are the brightest, easily outshining the only other naked-eye galaxy, Andromeda. Despite their familiarity, in December, a team of astronomers employing the Apache Point Observatory in New Mexico suggested that they may have been hiding something in plain sight all this time, that they are not two galaxies, but three. Since the 1980s, it had been speculated that the smaller of the two Magellanic clouds, imaginatively named the Small Magellanic Cloud, may in fact be a double. But thanks to Gaia, we now have accurate measurements of the motions of stars within the cloud. And thanks to the team, we also have precise snapshots of their chemical composition, both of which split the cloud into two equally sized components. Each, whilst appearing unified from Earth, are in fact separated by 16,000 light-years. This hasn't been officially declared, but it is a reminder of how much our universe is staring us in the face, unseen. Reaching out from our southern sky like a pair of spectral claw-tipped hands, the Magellanic Stream is one of the largest structures in our local group, spanning over 140 degrees of sky. A river of high-velocity hydrogen gas created by interactions between the Magellanic Cloud. The stream is divided into two filaments, each chemically and kinematically tied to one of the two clouds. The disturbed structure has hinted at moments in our galaxy's past, including a possible period of excitement by our own supermassive black hole. How it formed, whether through tidal disruption from interactions between the two clouds, or through compression by the interstellar medium, as the clouds plow through the universe at 400 kilometers per second, is still unknown. Regardless, there is no reason for the stream to be pristine. At least some stars should have been thrown into the stream as well. This Magellanic stellar stream has been sought for 50 years, but never found. Until this October, when a team headed by Vedant Chandra, a graduate student at Johns Hopkins University, identified 13 high-confidence members of the stream, spanning 100 degrees of sky. The stars are divided into two populations, a metal-rich population kinematically tied to the Magellanic Stream, and a separate low-metallicity stream of uncertain provenance. Locating them has also pinned down the size of the stream. It extends from 150,000 to 400,000 light-years from Earth. One wonders how a mind born around one of those stars would see its place in the universe. It is a fact obscured by our location and priorities, but the local group is not the Milky Way's local group. It is Andromeda's. The Andromeda galaxy is up to 5 times more massive, assuming the Milky Way's mass is as determined above, and contains up to 4 times as many stars as our home galaxy. In 4 billion years, it will collide with the Milky Way, at which point it will doubtless play the role of the dominant partner. And in October, a European and Indian team, utilizing some bleeding-edge modeling, were able to simulate the last time Andromeda consumed a circling paramour. There are certain elements, such as oxygen, sodium, and neon, that are primarily produced in Type II supernovae, the standard death of a giant star. Type II supernovae happen, well, not all the time, but frequently on a galactic scale. Type Ia supernovae, on the other hand, are much rarer, so the elements they produce, such as iron, manganese, and nickel, are only produced over a long period of time. Astronomers generally accept that Andromeda formed in two main bursts of star formation. The first, when the galaxy formed. The second, during a merger with a gas-rich galaxy, whose violent consumption about 3 billion years ago crushed that gas into new stars. Because chemical abundances form over different lengths of time, their presence or absence leaves a mark similar to a radiometric element like carbon-14, allowing astronomers to chart star formation over time. And what they found pretty much backs up that assumption. You may think Andromeda's history of less import than that of our own galaxy, but it is probably best to get to know someone before they arrive at your door and politely ask to eat you. The history of galaxies would appear to be one long, gluttonous, amorous orgy, as galaxies merge, birth stars in their union, and then merge again. But every party has its quitters. Hypervelocity stars are those whose velocities exceed the escape velocity of the galaxy itself, for our Milky Way about 550 kilometers per second, and hurl themselves into the intergalactic void. All hypervelocity stars known to date are hot, bright, and short-lived members of Type O and B. In November, a team led by Mar Carretero-Castrillo, a postgraduate student at the University of Barcelona, found, by employing Gaia data, that of the 417 O-type stars and 1,335 BE-type stars in the catalogs, 106 O-types, or about a quarter of the total, and 69 BE types, or about 5% of the total, were on their way out of the Milky Way. O and B type stars tend to form in close clusters called OB association. As such, over the years, two hypotheses have emerged about which event sends them on their course. The first is that one of the binary pair goes supernova, blasting its sibling off like a rocket. The second hypothesis is more peaceful, and suggests that stars can be gradually accelerated to extragalactic speeds through interactions with other stars in their birth cluster. Rather surprisingly, the gentler option disproportionately affects larger stars, and also results in higher escape speeds. Thus, the overwhelming preponderance of larger, brighter O-type stars in the sample lends credence to the already fairly widespread belief that the gentle hypothesis is the correct one. Nice to know that some things in astronomy don't involve cosmic-scale destruction and annihilation. One thing we do know about our galaxy is that, like 2/3 of all spiral galaxies, it has a bar. Some spirals are perfect pinwheels with simple circular bulges. Most, however, display distended bulges that stretch out into elliptical forms called bars. The standard hypothesis for the formation of a bar is that it forms gradually from the density waves that form the spirals in the first place. That said, there appears to be no correlation between a galaxy's possession of a bar and any of its intrinsic properties. A study this year suggests that the Milky Way bar, as it were, may instead have been the result of one of last year's list's most curious entries, the Gaia sausage. The Gaia sausage is a strange, elongated feature that appears on graphs plotting the radial velocities against circular velocities of stars in the Gaia dataset. Stars in this cluster have much faster radial velocities in either direction than stars in the galactic disk, and move in the opposite direction. Astronomers believe this population is the result of a gigantic collision our galaxy underwent between 8 and 11 billion years ago, during which our galaxy gained about 50 billion solar masses of material. While determining the age of the bar is difficult, a number of lines of evidence seem to suggest it is quite old, between 8 and 9 billion years, compared to 12 billion for the Milky Way itself. That age corresponds quite nicely with the Gaia sausage incident. Using computer simulations, the team modeled the evolution of our galaxy, both with and without the Gaia sausage collision, and found that the removal of the aforesaid encounter delayed the formation of our galaxy's bar by 2 billion years. The tidal tweak the added mass granted our galaxy's center was enough to tuck it into shape, giving it its singular grin. Sometimes I envy the minds of millennia past. They required so little to grasp wholly their place in the universe. If we tried to do the same, we would go mad. And yet, over time, ever larger fragments of it are coming into focus. Not enough, perhaps, but enough to keep us looking. If you enjoyed this second volume of my end of the year retrospective, and if you did, please remember to like, comment, and subscribe. And stay curious, fellow seekers.